Right, today we're going to talk about something very important called the moment of inertia. And before we even talk about the definition and things like that, we're going to write down two questions that I hope to answer by the end of this video for you. So, number one, what is meant by the term moment of inertia? And number two, why are moments of inertia important? So, take some time, write those two questions down, and by the end of the video, hopefully you can answer those questions and it makes sense. Okay? So if you need to pause the video at any time, just pause the video, and then when you're ready to go, just hit play and we'll be right here for you. So before we answer those questions, we have to go back and think about what we did in the fall when we were learning forces. So let's go back to some old knowledge, the old days. And it's always important to review where we have been, because then it's always nice to know where we've been and tie our new knowledge to our old knowledge. So the old days, sometimes you call this straight line motion, sometimes they'll call it translational motion or linear motion. We had sum our forces, and then we'd set it equal to m times a. So that's Newton's second law. And if we have a net force, that caused a net acceleration. And the reason we did this because we had sum our forces, and if we knew the mass, we could solve for the acceleration. And back in the day, it wasn't really like a question to know, like, hey, what's the mass? They just tell you 10 kilograms or 5 kilograms, and that wasn't really part of the problem. It's just like one of our givens that we just knew the mass. And then the cool thing is, once we knew the acceleration, we could go back to kinematics. Now, we're going to compare and contrast this, what we're going to do with the new stuff, the torque stuff, but you got to make sure this makes sense. So if that doesn't make sense, go back and think about forces, remind yourself, look at your notes to say, oh yeah, we summed our forces, we knew the mass, we get acceleration. Once you knew acceleration, you can go to kinematics and solve some different things about position and velocity. All right, so those are the old days. Sometimes you hear them referenced as straight line motion or translational motion or linear motion. That's just moving in a straight line. We applied a force to the center of gravity of the object and it moved in a straight line. All right, or it went down a ramp, or it did whatever, but it wasn't rotating. So the old knowledge is going to tie into our new knowledge very nicely, because we have the rotational analog to Newton's second law here is when we sum forces back in the day. Now we're going to sum torques. And now when you sum torques, the F's become torques, the A's become alphas, because instead of having like linear acceleration, you're going to have angular acceleration. This was in meters per second squared. This is going to be in radians per second squared. Okay, this is in newtons, this is going to be in newton meters. This was in kilograms, this is going to be a kilogram meter squared. We'll talk more about that. So the big thing is, in the new days, it'll be something that's rotating, so rotational motion. So these will be the rotational motion days. We'll have a point of rotation or an axis of rotation, and we'll be rotating about that point or axis. But we're going to sum our torques. So very similar, we used to sum our forces, now we're going to sum our torques. And if I is known, and that's the moment of inertia, that's what the focus of this video is, then we can solve for angular acceleration. But I wanted you to see these things side by side because we summed our forces, got the A, went to kinematics. Here we're going to sum our torques. We're still going to solve for A, it's just angular acceleration, so radians per second squared. And then we can use rotational kinematics. Okay, so, and the cool thing about rotational kinematics, that's very, very, very similar to the translational kinematics that you're used to. So we have that, but let's talk about those two questions now. What is meant by the term moment of inertia, and why are moments of inertia important? We're going to talk about those right now in context of what we just learned right there. Number one, and I had a drop of water land on my notes today. It's very frustrating. I was trying to stay hydrated, do all the right things, but write down the definition of moment of inertia. And it's kind of a definition, but it's more of an explanation of what it is. The moment of inertia depends on the mass or masses making up your system and how far that mass is from the axis or point of rotation. Short answer, a moment of inertia, yeah, it depends on mass, but it also depends on where that mass is relative to the point of rotation or the axis of rotation. Okay, so that's very, very important to know. Back in the forces days, it just mattered, I have a force, I know a mass, I can solve for acceleration. In the rotational days, I have a torque, I have a moment of inertia, which depends on mass and how that mass is distributed, and that'll lead me to have a certain angular acceleration. So it's very similar. Moment of inertia is like mass, but it's just how that mass is distributed about your point of rotation. And we're going to talk more about that. Our textbook kind of lays it out this way in the blue, and then I put this down because I thought it was a kind of a nice way to put it. A measure of the rotational inertia or resistance to being angularly accelerated. So if you picture like a soup can and you're putting a force on there and you're trying to make it roll, the moment of inertia is like the resistance to wanting to be rotated. Back in the day, A equals the sum of your forces divided by your mass. If you had a large mass, for a certain net force here, your acceleration would be smaller. It's the same here. If you solve for angular acceleration, it's the sum of your torques divided by moment of inertia right there. So if you had a large moment of inertia, torque divided by a large number here, then you'd have a small angular acceleration. So it's just important to keep in mind that moment of inertia is your resistance to being rotated. Big I means it's going to take a great torque to make it rotate. A small I means it's going to rotate more easily. So the answer to question number 2, why are moments of inertia important? They are important because we can then figure out how an object rotates. And how an object rotates could be as simple as looking at kinematics. It could be looking at kinetic energy of rotation. It could be looking at angular momentum. But once we know the moment of inertia, we can figure out a lot of things about how that object is rotating. So we hopefully answered what a moment of inertia is, and number 2, why moments of inertia are important. And now we're actually going to do some work with moments of inertia. We're going to find them. So we're going to find some moments of inertia, and I'm going to show you 2 ways to do this. However, you should know there are more, but on the AP physics test and things like that, these are 2 of the fundamental ways they talk about when we have discrete moments of inertia and then continuous. For discrete masses, it's very, very cool. If you want to find the moment of inertia, you just sum them up, you just add them up. So this is the Greek letter sigma, and the formula for moment of inertia, it's whatever mass you're talking about times how far away that mass is from your point of rotation squared. I'll explain this, then we'll do some examples. It'll make a lot more sense. All right, so you have the first mass, then times how far away that object is from the point of rotation, and don't forget to square that distance. And if you had 3 objects, you'd take the moment of inertia of the first one plus the second one plus the third one. And I really made a note here. I said you add up individual moments of inertia to get the total moment of inertia about some point of rotation. But the key thing is you can do this, you can add them up as long as they're about the same point of rotation or the same axis of rotation. I said you just add them up. They're different contributions. It was so important, I wrote it, and then I'm like, I'm gonna write it again so I don't forget to mention it in the video. All right, so that's the formula for discrete masses. That's a sigma summation. You're just gonna add up their different contributions. So let's do some examples here. An orbiting planet, and now really important, what do physics people mean by a point mass? So a point mass could be like this green dot right here. This is some planet, you can name the planet whatever you want, and let's call the point of rotation, it's orbiting about the sun right there. It's got some R value right there from the center of the planet to the center of the sun. And this mass is highly concentrated right there in some kind of sphere, and it's orbiting about the sun. So that's a point mass, just a point of mass in space. Or it could be a little tiny particle. In this case, we're doing large things, but it's some distance r away from the point of rotation right there, and it's got all of its mass concentrated in like this little spherical bundle. Okay, so if you want to find the I of the planet, the moment of inertia of a planet, well, this is pretty easy. Here's your point of rotation. It's r away, and let's just call the mass of the planet mass planet. I'm really creative, MP. All right, so if you want the moment of inertia of that one planet, you'd say, all right, the I of the planet equals its mass times how far away it is squared times r squared. mr squared. And I just have a subscript p for mass of the planet, but it's just mr squared. That's a point mass. Even though it's large, it's just a singular point, right? That we're treating the planet like a singular point. All right, that's example 1. Let's look at example 2. We'll take it up a notch. Well, what happens if you have a 2-mass system? So here's our axis. And now this is a point of rotation, right? It was orbiting about this point of rotation right there. Now we're gonna have an axis of rotation. So we have some rod, boom, and at one end of the rod we have mass m. Other end of the rod we have mass m. Now very important. Here's the axis of rotation right down the middle of the rod, and the rod is length L, so this is right down the middle of the rod right there. We have to add up the moment of inertia of this 2-point mass system, and we're just going to follow our formula. If you want the I, boom, it's going to be this mass right here. You know, if you want to call them, you know what, we'll call it mass 1, we'll call this one mass 2, and let's make a note here that m1 equals m2, just so I can show my steps here, and we'll say equals m overall, so don't let that mess you up. So we're going to add up the contribution of m1, so we'll say m1. Now m1 is how far from this axis of rotation. This whole length is L, so m1, and we're saying this is spiked right down the middle, so this r value here will be times L over 2. L over 2, half the length of the rod squared, plus, that was the contribution of that object, that point mass right there, plus this point mass right here, so m2 times L over 2 squared, and you're like, okay, it's going to be m1 L squared over 4 plus m2 L squared over 4 equals, and I made a little note here, m1 equals m2, and this column m, right? So let's just say m L squared over 4 plus m L squared over 4. That'll be 2ml squared over 4. So your final answer will be ml squared over 2. That is your moment of inertia for the 2-point mass system. And I put this little thing like it's rotating, you know, counterclockwise there. I will say you're just adding up, and the cool thing, the reason you can do that, you're just following your formula, and It's because it's about the same axis of rotation right there. You just add up their individual contributions. I only put the M1 and M2 in there just to show you that was that one's contribution, boom, plus that one's contribution. And then I just said, oh, but M1 equals M2, ML squared over 2 for the moment of inertia of that system. Keep in mind, if you know the torque of the system, you know the moment of inertia of the system, you can solve for the angular acceleration of the system. That's the big goal eventually, okay? I just want to finish by doing a tougher point mass example. So we have a blue mass, a green mass, a blue mass, and a green mass. And the blue masses are B away from the point of rotation right here. And I should put a little star here, the point of rotation. Boom, just like that. The green masses are a distance or separation A away from the point of rotation. Question letter A, what is the I if the system here is rotated counterclockwise in the plane of the paper? So picture this 4-mass system. We're going to rotate it. We put a force at a radius, which is a torque, and we're going to try to rotate it, boom, counterclockwise. So the moment of inertia that we have to calculate is the contribution of this green mass plus the blue one plus the green one plus the blue one. So if you want to find that I right there, it's the mass of the green one, M, and that green one is A away. So MA squared, we treat it as a point mass. Boom, that's the contribution of that one. Then we have the mass of this blue one right here, plus the mass of the blue one. Let's call it, let's say they're equal masses. Mass of the blue one times B squared, because that's how far that is away from the point of rotation. And then part of the system as well is this mass right here, M times A squared, plus the mass of this one times B squared. So if you wanted to rotate this system, 1, 2, 3, 4, these 4-point masses in the counterclockwise direction, you literally have to move all of them about that point right there. And that's why the moment of inertia is so large. It's going to be combined like terms, 2ma squared plus 2mb squared, because you are literally trying to move all 4 of those masses. Maybe you're going to put your force here, or put it here. We'd have to talk about that. But we know the moment of inertia of this 4-mass system is 2ma squared plus 2mb squared. Now, the question can change a little bit. Part B, it says, well, what's the moment of inertia if the vertical axis was fixed? So instead of it being this point that was fixed, what happens if you fixed this axis right here, and you said instead of it rotating in the plane of the paper, let's fix this axis right here, and let's rotate, this mass right here and this mass right here, and can you picture it becoming in and out of the plane of the paper? Like this one would come in, out of the paper, this one would go in, and then eventually it would come back around just like this. So you're not trying to move all the masses because we're going to fix it about the vertical axis right here. So if that were the case, we just want to find the I if the vertical axis were fixed. And we'll say right here, okay, well that's the case, then we're going to try to move this one, the mass, times b squared. As this one moved out of the paper, this one would be moving into the paper, plus mb squared equals 2mb squared. And if you look at that, you're like, oh, the moment of inertia is less. Well, yeah, that makes sense because you're not moving the green ones as well. If you fix this axis right here, you say it can only rotate freely in and out of the paper. Well, your moment of inertia, just like you have less mass in your system, we're talking about forces. Well, now you have less moment of inertia, or smaller moment of inertia, because those are fixed right there. You're essentially R equals 0. So you're not planning on moving them in this situation. And the final question is, what happens if you fix it about the horizontal axis? So if you fix it about that axis right there, we cover it up because that's the axis now. And we say, oh, that means this green one can come out of the paper, and this, as that green one comes out, that green one goes in. So these are your only 2 masses rotating. So we'll say, hey, let's go green. It'll be ma squared. That's the first green mass. So this green one, we're going to put a torque so that it causes it to rotate in and out of the paper. This one's coming out at you. This one's going in. So ma squared plus ma squared again. The contribution of other mass, which is 2ma squared. Boom, for your moment of inertia right there. So it kind of makes sense. I started when you're trying to rotate it, the whole system in the plane of the paper, and you literally have to have the moment of inertia of this object plus that one plus that one plus that one, because you are trying to move all 4 of them. All right, that's the point of rotation one, and that's why the moment of inertia was so large. And then I said, hey, what if you fix the vertical axis? Well, if you fix this axis right like that, and this one we're going to rotate it so this one comes out and that one goes in, well, now you're only moving 2-point masses, so that's why your moment of inertia was less, 2mb squared. And to finish, we said, all right, let's fix this horizontal axis. And it doesn't make sense to say let's try to rotate it counterclockwise anymore because it's a fixed axis right there. So we say, all right, let's try to rotate this one out of the plane of the paper, and that means that one will go in. And if that's the case, ma squared plus ma squared is 2ma squared. Okay, so that's about as tough as the discrete point mass moment of inertia questions get. But same thing rings true. You're just adding up point masses about a point of rotation or an axis of rotation. So thanks for watching.